So in this video, I want to finish up with bond hybridization by talking about what's called sp hybridization. But first I want to finish up with our discussion on sp2 hybridization. All right, so let me switch over here. Okay, so when we finished up here, this is the model that we had made of an sp2 hybridized carbon. All right, and again, this is actually this is a molecule of ethene, where there's two carbons here, which are both sp2 hybridized, and this is the structure that we would normally draw for ethene. And you notice that when we do the structure, when you do a double bond, it makes it look like the two bonds are entirely equivalent to each other, but in reality these bonds are fundamentally different. All right, one of the bonds that you would have, one of the bonds is essentially a sigma bond. All right, it's going to be this central bond right here, and that's a sigma bond because it's created by the head-to-head overlap of two separate sp2 hybridized orbitals. One of those orbitals belong to this carbon, one of those belong to this carbon, and when they overlap they create that region in the middle, and that's what one of the single bonds is. The other bond is a pi bond. All right, and that's what it comes from the overlap between these two. So this is my fingers are touching one of the p orbitals. Now they're touching a p orbital on the neighboring atom, and those p orbitals, when they're side by side, can overlap with each other. All right, and that's what the yellow tape represents. It represents where the electrons would be shared between those there, and that's what the second of the bonds in the double bond represents. All right, so one thing that you notice about this is that there are 4 hydrogens that are attached, and if you remember Vesper theory, you would be able to figure out that the orientation around the carbons is trigonal planar. All right, so how that works, notice one thing I haven't done yet is we've still got these sp2 hybrid orbitals on each of the carbons, and if I take a hydrogen atom and that sp2 hybrid orbital and I let them overlap, that would create a sigma bond between those two atoms. I could do the same thing here, and here, and there you would have that orientation, that trigonal planar orientation between this hydrogen, and this carbon. Notice that those would form that trigonal shape, and it's planar because it's a flat structure. All right. So one thing I want to point out is that pi bond that you have is actually in the plane of the would be in the so if I hold it kind of in the way it's drawn, the sigma bond, which is the thing in the middle, is in the plane of the paper, but the pi electrons are actually coming out, would be perpendicular. All right, so there's the pi electrons, but if I turn it so that it's in that orientation, notice that they're coming towards you. All right, and that's a little bit, obviously we're not going to be able to draw molecules if we draw this in a spatially correct way, because it would require a 3-dimensional drawing, and we're not going to be able to do that. But just keep in mind, that's what the double bond represents. So moving on to the last type of hybridization, it's what's called sp hybridization. And this is the type of hybridization that you're going to get whenever you have triple bonds. All right, so triple bonds are fairly rare in organic molecules. I mean, you do run into them, but not nearly as much as double bonds and single bonds. All right, so the way this is going to work, again, we're going to start from that state where we've had one of these electrons, which has been promoted to the 2p level. All right, and this time when all of these orbitals hybridize, 2 of them are going to make these sp hybridized orbitals, and 2 are going to remain as unhybridized orbitals. They're going to remain exactly like they would be if they were just the regular pre-hybridized orbitals. All right, again, notice that these p orbitals are at the same energy level as the original ones, but the hybrid orbitals are somewhere between the energy of the original s orbital and the original p orbitals. All right, so this is what an sp orbital looks like. Notice it looks just like the sp3 orbitals. And when you have two of them, all right, the way that they're going to overlap is essentially in a straight line. All right, so this right here, I've kind of tried to shade it a little bit. I could probably zoom in a little bit on that. All right, you'll notice, okay, this right here would be one of the orbitals, right? And then this right here would be another of the orbitals. And that's essentially they're gonna bond in a 180-degree angle to each other. All right. So then what we're going to do is we're going to take two separate p orbitals and we're going to orient them perpendicular to this. All right. So let me show you a model of that. Okay. So far, this right here would be a model of this particular part right here, where each of these lobes would essentially be, this would be two separate orbitals, all right? They would be the sp orbitals. This would be one of them. We'll call one of them the left and one of them the right, all right? And so what we're going to do is we're going to end up putting two separate p orbitals onto this, all right? So again, this is essentially what a p orbital would look like, all right? And so let's put, okay, let me go ahead and put the, okay, so I wish I had a better model kit because it makes it look like these are all the same. All right, what I'm trying to show here is this right here. My fingers are on one of the p orbitals. This right here is an sp orbital, and this is a different sp orbital. All right, so remember there's two p orbitals that are part of this, so I need to put the second one on. So again, if this is one of our sp orbitals right here, and this is another of our sp orbitals right here, all right, my fingers are now touching one of the unhybridized p orbitals, and holding it this way, my fingers are holding the second of the p orbitals. All right, so notice that the those two p orbitals are essentially equivalent to each other, because if I just rotate the atom, they're exactly the same thing. All right, so what are we going to do with this? This is used whenever we have triple bonds. All right, so what I'm going to do is I'm going to make an exact copy of this guy. Okay, so the molecule that we're going to be making here is the one showed right here. It's called ethine. All right, it's actually more commonly called acetylene. All right, welders use it in acetylene torches, but it's the most famous molecule that's got a triple bond. All right, so the carbons that are in that are going to be sp hybridized. All right, so I've got two equivalent copies of that sp hybridized carbon. And again, when you look at one of these, all right, the way I'm holding these is I've got my fingers on those two separate sp orbitals. All right, this is a regular p orbital. This is another regular p orbital right here. But this hand right here, one of my hands is touching one of the sp hybrid orbitals and one is touching the other. All right, and so what can happen is these things can overlap like this. All right, so two of those sp hybrid orbitals can overlap in a head-to-head fashion. All right, so therefore that creates that sigma bond. All right, so I'm going to connect those. Okay, so those are now connected. So this right here in the middle, that is now a molecular orbital. All right, there used to be two separate atomic orbitals. It's now a molecular orbital. All right, notice we have, this is an atomic orbital. That's an sp orbital that hasn't been bonded yet, but we know that there's a hydrogen that it can make a bond with. So you take the atomic orbital from the hydrogen, the atomic orbital from this carbon, and those now overlap to make this molecular orbital. Same thing can be done on the other side. And that is, notice when you have the triple bonds, we would expect those to be linear. All right, and notice how all of those are in a straight line. All right, so right now we've only talked about one of the bonds. So where do the other two bonds of the triple bond come from? All right, they're going to come from pi bonding. All right, we've got these. This is my fingers are on one p orbital. These fingers are on a different p orbital. And notice those are right next to each other. And electrons can be shared between these p orbitals. So I'll represent that with a little tape. Okay, so the yellow tape now shows that pi overlap. One thing I want to point out is that the yellow tape actually represents only one of those 3 bonds in the triple bond. All right, so I know that there's 2 separate pieces of tape, one for the part that's above and one for the part that's below, but combined, that is considered to be 1 bond. All right, and so where is the 3rd bond going to be? Well, if I turn it this way, you see that there are now these 2 other p orbitals, and those can overlap to make a pi bond. Okay, so there was one of your pi bonds, and now I'll use a little green tape to show the overlap between the other p orbitals, making a 2nd pi bond. All right, so even though when we draw this molecule, it looks nice and clean, where you've just got 2 carbon atoms triple bonded and you've got the 2 hydrogens, what that actually means is a sigma bond between this carbon and this hydrogen. That bond was an sp hybridized carbon. It was made from an sp hybrid orbital of the carbon with an s orbital from the hydrogen. Same thing over here. That's one of the hydrogens right there. Notice that the Vesper theory still works. All right, we would predict that particular molecule would have a linear triatomic arrangement, and the bond angle between that hydrogen, this carbon, and this other carbon right here, that is a straight line. All right, all of these atoms are in a straight line. All right, as far as the triple bond goes, one of the bonds in the triple bond is a sigma bond, which is that one in the one in the middle right there. You can see my pencil touching it. All right, that's formed when 2 of those sp orbitals overlapped head to head. All right, but then the 2 other bonds in the triple bond are pi bonds, which are the overlaps from the p orbitals. All right, so the yellow one would be one of the bonds, and the green ones would be another. And one thing I want to point out while I have this model is that whenever you have double and triple bonds, you no longer can have rotation around the bond. All right, and that's going to be different from single bonds, because single bonds will allow rotation, and that'll become a big deal when we talk about isomers in the next unit.